explainer. Today, we're diving straight into organic chemistry to discover exactly how the entire physical world is built from molecular Legos. If you've ever looked at a really complex chemical structure and felt like you were trying to read an alien language, well, you are in the exact right place. We're going to decode that language together, starting right at the absolute basics. So here's our roadmap for decoding all this. 1. Meet the hydrocarbons. 2. The universal chemical code. 3. Alkanes and single bond stability. 4. Synthesizing and reacting alkanes. And finally 5. Alkenes, alkynes, and unsaturation. Let's get right into it. Section 1. Meet the hydrocarbons, the true foundation of organic matter. It's honestly amazing. Just two elements, carbon and hydrogen, linking together to create almost infinite possibilities. We're talking about the literal building blocks of life, the fuels that power our cars, and the foundation of the plastics we use every single day. If you understand hydrocarbons, you basically hold the key to understanding all organic molecules.
Check out this breakdown. We classify these guys simply by their bond types. You can see alkanes rely entirely on single bonds, following that CnH2n+2 pattern. But as we introduce double bonds, we get alkenes, and with triple bonds, alkynes. Every single time we add a bond, we drop a couple of hydrogen atoms from our formula. It's a beautifully logical system once you see it laid out.
Moving to Section 2, the Universal Chemical Code, also known as IUPAC nomenclature.
Think of these 5 IUPAC rules kind of like addressing a letter to a very specific house. First, you find the longest continuous carbon chain. That's your parent chain, or the state. Then, you number that chain to give your substituent groups the lowest possible number. That's your street. Next, identify your substituents and assign them those numbers. Those are your house numbers. And finally, you just put the whole shebang together in alphabetical order.
Seeing that second rule in action is actually pretty cool. If you look at this 8-carbon chain and just read it left to right, you might totally think the branching methyl group sits at position 7. But if you follow the numbering from right to left, you'll see we hit the branching group at position 2. We always want the lowest possible number for sure, so numbering from right to left is the correct chemical address here.
Now, to actually name that parent chain we just looked at, you're definitely going to want to memorize these prefixes quickly. They tell us exactly how many carbons are in our primary structure. 1 carbon is meth, 2 is F, 3 is prop, and 4 is bute. Honestly, once you hit 5, it gets a bit easier, because it just follows standard geometric shapes like pent for 5, hex for 6, all the way up to dec for 10.
Now here's the catch. Molecules will sometimes try to trick you. Notice how the true longest continuous chain actually bends downwards, rather than just going straight across from left to right. Molecules aren't just rigid lines on a page. They bend, they twist. So always trace the absolute longest, unbroken path of carbons, even if you literally have to turn a corner to do it. Okay, Section 3, alkanes and single bond stability. So when we say saturated, what we really mean is that their carbon atoms are completely maxed out with hydrogen atoms via strong single bonds. We call these sigma bonds. Because there's literally no room left to add anything else without breaking those tough sigma bonds, alkanes are incredibly reliable and relatively inert. They don't just react with whatever they happen to bump into. Which brings us to Section 4, synthesizing and reacting alkanes. Catalytic hydrogenation is absolutely one of our primary tools here. Basically, this process just forces hydrogen gas onto an unsaturated molecule. By using a metal catalyst like platinum, palladium, or nickel, the reaction breaks down weaker double or triple bonds and totally saturates the carbons with hydrogen. It effectively turns an alkene or alkyne into a nice, stable, single-bonded alkane. But hey, what if we want to build a bigger molecule completely from scratch? Well, that's where the Wurtz reaction comes in. It acts literally like molecular glue. By using highly reactive sodium metal in a dry ether solution, we can take 2 smaller carbon chains, specifically alkyl halides, and forcefully snap them together. The sodium bonds with the halides, and the 2 carbon chains couple up to form a much larger alkane. It is a fantastic way to double your chain length.
But what about breaking alkanes down? Since alkanes are so incredibly stable, forcing them to react requires some pretty intense conditions. I mean, you essentially have to torture the molecule. You can combust them with oxygen, which releases massive amounts of heat, water, and CO2, which is exactly what happens inside your car's engine. You can use intense UV light for halogenation to forcefully swap a hydrogen for a chlorine or bromine, or you can use extreme heat
to literally crack them, breaking massive alkane chains into smaller, much more usable pieces. So we've seen how stable single bonds are, and the sheer force required to break them. But let's shift gears for a second and ask, what happens to our molecular Legos when we intentionally introduce unsaturation? What if they aren't entirely satisfied with just hydrogen? That takes us to section 5, alkenes, alkynes, and unsaturated